Network loss. In this topic, we will talk about KCL and KVL. KCL is Kirchhoff's current law and KVL is Kirchhoff's voltage law. Let's talk about KCL first. Consider a point where different circuit elements are connected. Let I1, I2 and I3 as incoming current and I4 and I5 as outgoing currents. One direction of current we will take positive and other direction we will take negative. Outgoing current is the current coming out of node and is taken positive. And the current going towards a node, that is incoming current, is taken as negative. This point is called a node where two or more elements are connected. Here, I4 and I5 are outgoing currents and taken positive, and I1, I2 and I3 are incoming currents that are taken negative. Therefore, according to KCL, algebraic sum of currents at any node or junction is equal to 0. Therefore, minus I1 minus I2 minus I3 plus I4 plus I5 is equal to 0. Solving further, we can write I4 plus I5 is equal to I1 plus I2 plus I3. That is, the sum of outgoing currents I4 and I5 is equal to sum of incoming currents, that is I1, I2 and I3.
In KCL, we have conservation of charge. Where current entering a node is equal to sum of current leaving a node. And in KVL, we have conservation of energy, where algebraic sum of all voltages in a single direction or loop is 0. Using KVL, we do mesh analysis, and using KCL, we do nodal analysis. Let's talk about KVL. Let's first look at the polarity of the voltage across the resistance. We know that current in the resistor flows from higher potential to lower. Therefore, considering the direction of current from where current enters in the resistor is taken as positive and where it leaves is taken as negative. In KVL, voltage across the resistor is always decided by the later terminal. If you consider current in this direction, then this terminal is positive and this is negative. Therefore, voltage will be negative. And if you consider this direction, then this will be positive and this terminal will be negative. In this case also, voltage will be negative. Next, look at the polarity of the voltage source. While applying KVL in the circuit, if the direction of current considered in such a way that it is moving from negative to positive terminal, then there is voltage rise across voltage source. Therefore, voltage is positive. Current is moving from positive to negative terminal, then there will be voltage drop and voltage is considered as negative. That is, the later terminal decides the polarity of the voltage source. Here, the later terminal is positive. Therefore, voltage is positive. And the later terminal here is negative. Therefore, voltage is negative. Now, let's consider a circuit where current I flowing in a clockwise direction. According to KVL, sum of voltage in a loop is equal to 0. Therefore, V1 plus V2 plus V3 plus V4 is equal to 0. Now, according to direction of current, there will be voltage rise across V1. Therefore, V1 will be positive. And as per the direction of current, therefore, due to voltage drop, V2 will be negative. There will be voltage drop across V3 as current going from positive to negative terminal. Similarly, there is voltage drop across this resistor also. Therefore, V4 will be negative. As it can be seen, there is voltage rise across V1 and voltage drop across V2, V3 and V4. Therefore, positive V1, if this is resistance R1 and this is R2, then minus IR1 minus V3 minus IR2 is equal to 0, or V1 is equal to V3 plus I into sum of R1 plus R2. That is, voltage rise across V1 is equal to sum of voltage drop across V2, V3 and V4. Now, let's look at some key points that will help you to solve problem while using KVL in the circuit. In a loop, if current Ix flowing out of voltage source V1, then same amount of current, that is Ix, will come back to voltage source V1. Now let's see another example. Let's introduce a current source in place of R2. We cannot apply KVL in this loop as we do not know the value of resistance of current source and hence cannot find the voltage across it.
In the next case, short circuit the resistor R3 and voltage source V2 as current follow the path of least resistance. No part of current Ix will flow through resistance R2 and R4 and the entire current Ix pass through the short circuit. Here it is good to note that short circuit nullifies the parallel resistor as no current passes through the parallel resistor in presence of short circuit. Similarly, this short circuit nullifies R4 and R2 and the new modified circuit will be as shown.
Now let's take a closer look at the nodes and branches of a circuit and how KCL and KVL equations are related to them. Consider a basic circuit having voltage source V1, V2 and circuit element as resistance R1, R2, R3, R4 and R5 which are connected to N1, N2 and N3 at ground. Therefore, total number of nodes is equal to 3. Node considered at the ground is called reference or datum node. In addition to node, we have branches. Branch is basically a connection between two nodes. Between N1 and N3, we have two branches, that is B1 and B2, where B1 includes R1 and V1 and B2 includes only R2. Between N1 and N2, we have only branch B3 that includes only R3. Similarly, between N2 and N3, we have branch B4 and B5. Here, total number of branches is equal to 5. If we know number of nodes and branches, we can easily find out number of equations for both KCL and KVL. Number of KCL equations is equal to
n minus 1, and number of KVL equations is equal to b minus n minus 1. That is, b minus number of KCL equations, where small n is total number of nodes in a circuit, small b is total number of branches. Therefore, as per shown circuit, we have small n is equal to 3. Therefore, number of KCL equation 3 minus 1 is equal to 2. For number of KVL equations, we have b is equal to 5 and n is equal to 3. On putting the value of b and n in above formula, number of KVL equations comes out equal to 3. Let's apply KVL in a circuit and do mesh analysis. Consider the shown circuit. This circuit has 3 mesh, 1, 2 and 3. Here we have to consider one direction of current, either clockwise or anti-clockwise. Using that, consider voltage drop or rise across the voltage source. Let's consider clockwise direction in mesh 1. For mesh 2, we can take anti-clockwise direction of current I2. Similarly, for mesh 3, where current direction is taken as anti-clockwise. Let's make an equation for mesh 1. Current in R1 is I1, current in R2 is I1 plus I2, as current in R2, that is I1 and I2, are in same direction, which is downwards. On applying KVL in mesh 1, that is sum of voltages in single direction is equal to 0, where V1 is positive due to voltage rise. Due to voltage drop across R1 minus I1 R1, and similarly there is voltage drop across R2. Therefore, minus I1 plus I2 into R2 is equal to 0. On solving equation, V1 comes out in terms of I1 and I2. Now let's consider mesh 2. Current in R3 is I2 and current in R2 is I1 plus I2. Current in R5 is I2 minus I3, because
In this case, current I2 and I3 are in opposite direction. Therefore, where direction of current I2, that is anti-clockwise, is considered positive in case of mesh 2. Therefore, opposite direction of current I3 become negative. On applying KVL in mesh 2, there will be voltage drop in R2, R5, and R3. Therefore, KVL equation for mesh 2 comes out in terms of I1, I2 and I3. And similarly for mesh 3, where current in R4 is I3. Here current in R5 is I3 minus I2, as direction of current I2 is opposite, where I3 direction is considered positive and I2 direction is considered negative. On applying KVL in mesh 3, due to voltage drop across R4, we have minus I3 R4 minus I3 minus I2 into R5, which is due to voltage drop across R5, plus V2 due to voltage rise, as current flowing from negative to positive terminal. Therefore, KVL equation for mesh 3 comes out in terms of V2, I3 and I2. Next is nodal analysis. Before moving to nodal analysis, first map out some of the difference between mesh analysis and nodal analysis. As discussed before, in mesh analysis, where we do KVL, we consider one direction of current, and that current becomes circuit variable for that mesh. In nodal analysis, node voltage becomes a circuit variable. Here, in mesh analysis, KVL equation comes in terms of circuit variable, that is I1, I2, I3 and so on for n meshes. Similarly, for node voltages, equation comes in terms of circuit variable. Now let's check the difference between the procedure. In mesh analysis, we first assign mesh current to every mesh and apply KVL to make equation in terms of circuit variable, that is mesh currents. In nodal analysis, we apply KCL on a node and using Ohm's law, we make equation in terms of node voltages. Here, it is good to see how to find current due to potential difference between two nodes. Let's consider two nodes having voltages V1 and V2 connected with a resistance R. If V1 is greater than V2, then current will flow from V1 to V2 as current flows from higher potential to lower. Therefore, V1 minus V2, then as per the direction of current, voltage drop across the resistance, that is minus IR, is equal to 0. Similarly, if we apply voltage source between two nodes and if current is moving in this direction, voltage between two nodes A and B is VA minus VB minus 5, as there is voltage drop, is equal to 0. Therefore, VA minus VB is equal to 5. If current I2 flows in opposite direction, then VB minus VA plus 5 due to voltage rise is equal to 0. Therefore, VB minus VA is equal to minus 5 multiplying by minus 1 on both sides. We have VA minus VB is equal to 5 or VAB is equal to 5 volts. Similarly, if we have both resistance and voltage source, and if current is flowing in this direction, then VB minus VA plus 3 due to voltage rise minus IR due to voltage drop is equal to 0. Therefore, VB minus VA is equal to IR minus 3. On multiplying by minus 1 on both sides, VA minus VB comes out equal to 3 minus IR. Similarly, if current flowing in opposite direction, then we have VA minus VB minus IR due to voltage drop. Similarly, we have voltage drop across 3 volt supply. Therefore, minus 3 is equal to 0, or VA minus VB is equal to IR plus 3. Now, let's start with nodal analysis. In the shown circuit, let current I1, I2 and I3 are flowing in respective branches, and if this is node N1, on applying KCL at node N1 and considering I1, that is incoming current, as negative, similarly I2 and I3, that is outgoing currents, as positive, then minus I1 plus I2 plus I3 is equal to 0, or we can write as I1 is equal to I2 plus I3. If voltage at node N1 is Vn1 and voltage at node N2 is Vn2, then current I1 due to potential difference between V1 and Vn1 can be calculated as shown, that is V1 minus Vn1 minus I1 R1 due to potential drop across the resistor is equal to 0. Next is current I2, which is due to potential difference between Vn1 and ground, that is at 0 volts, and as discussed before, it is also called as reference or datum node. Therefore, we can write I2 is equal to Vn1 minus 0 divided by R2. Similarly, we have I3, which is current due to potential difference between Vn1 and Vn2, and it can be calculated as shown. Vn1 minus Vn2 minus I3R3 is equal to 0. I3 is equal to Vn1 minus Vn2 divided by R3. If this is equation 1, this is 2, this is 3, and this is 4, then using equation 2, 3 and 4 in 1, we get KCL equation in terms of node voltages Vn1, Vn2 and supply voltage V1. On considering the current for second half of the circuit, that is current I4 and I5 as shown, on applying KCL at node N2, we have I3 as incoming current and taken as negative, also I4 and I5 as outgoing current
which are taken positive.
Therefore, minus I3 plus I4 plus I5 is equal to 0, or I3 is equal to I4 plus I5.
As discussed before, I3 is equal to Vn1 minus Vn2 divided by R3. Similar to I2, we can calculate I4, that is current due to potential difference between node Vn2 and ground. Therefore, Vn2 minus 0 minus I4 R4, that is due to voltage drop across the resistance, is equal to 0. Therefore, I4 is equal to Vn2 by R4. I5 is current due to potential difference between Vn2 and V2. I5 is calculated as Vn2 minus V2 minus I5 R5 is equal to 0, or I5 is equal to Vn2 minus V2 divided by R5. If this is equation 5, this is 6, this is 7, and this is 8, then using 6, 7, and 8 in equation 5, we get the KCL equation in terms of node voltages Vn1, Vn2 and supply voltage V2.